Welcome to the course on advanced machining process. Today we are going to discuss on electrochemical machining process. So as the name suggests, it is a electrical type non-traditional machining process. This ECM process works on the principle of Faraday's laws of electrolysis. So all of us we know that this electroplating operation where atom by atom that some metal is deposited on a electrical conducting material. So it is a reverse of this electroplating operation. So here this metal is removed from the anode or from the workpiece atom by atom. So this process, it is very useful in industry. So in many industries like nuclear industry, aerospace industries, they use this process for machining of very high strength temperature resistant material, and also this process also useful for machining of very complex surfaces. So you have to generate a tool which is prototype of the tool shape. Actually it is a replica of the workpiece to be made on the workpiece surface. So in ECM process there is no wear out of this tool, like in EDM process there is a wear out of the tool, but in EDM process there is no wear out of tool. So wear out of tool is very low or it is not there. So like in EDM process, that kind of relative electrode wear rate, that thing are not there in ECM process. So now we shall discuss how this electrochemical machining process works. So that working principle of this electrochemical machining process. So you can see that this is the circuit where there is a DC battery is attached here. So this is the cathode and this is the anode here. So here electrical energy is transported through, in metals it is transported through by conduction of electrical charges, but in salt solution it is electrical energy is transported through the migration of ions. So in electrolytic cell, DC battery sends electrical current to the molten NaCl salt. So here this molten NaCl salt is there. So it is connected through a DC battery. So here left hand side this is the cathode and right hand side this is the anode here. So now NaCl salt is there inside that container and this current is flowing because of it is connected to a DC battery. So now electrons from this DC power supply, it will come to the cathode, and then this sodium plus ion, so these cations actually it will attracted to the cathode and it will be reduced here at the cathode. So it will become sodium and it will be deposited on the cathode. And then chlorine ion present in the chlorine, that is negative ion, so anion which is present here in the solution. So it will come to the anode here and it will release one electron, and then this electron will come to this battery, and again through this battery this electron will be pumped to the cathode, and now this electrical circuit actually it will continues. So now you can see here these equations. So sodium plus, it takes that electron here and it is reduced here at the cathode and it will become sodium metal atom and it will be deposited at the cathode, and chlorine ion, that is negative ion, it will be attracted towards the anode here and it will release one electron and it will generate this chlorine gas. So in electrolytic cell, DC battery sends electrical current through the molten and sodium chloride salt. So electrons from the batteries enter melt at the cathode and leave melt at the anode, returning to the battery. So like this total circuit actually continues. This power supply continues through this electrolyte. Sodium plus from the salt combine with the electrons at the cathode and produce sodium metal which accumulates at the cathode, and sodium plus which is reduced here. So, reduction operation means addition of electrons at the cathode. So, it is reduced here, sodium plus it is reduced here at the cathode, and chlorine it migrates towards the anode and it is oxidized. Oxidized means electrons is released to the cathode and to become this chlorine gas. So, for getting the sustained flow of current and to avoid accumulation of ions at the electrode, reactions must keep on occurring at the electrode to maintain the electrical neutrality. So this battery, DC battery source should supply power, and so it will generate the sustained flow of current and it will avoid accumulation of ions at the electrode. So this external circuit feeds the electrons into the medium at the cathode, that is electrons, that is the DC battery here, and these electrons are consumed at the cathode by the cations. Here it is sodium plus ion, since they migrate to the cathode, and electrons are released by the negative ions, that is chlorine ion of medium at the anode. So like this reaction continues. So this is the typical electrolysis process for sodium chloride solution. Now in electrochemical machining process, this electrolysis like electroplating, electroforming and electropolishing, these all are actually electrolysis process. So this ECM process, electrochemical machining process, metal removal by electrochemical dissolution, so or anodic dissolution, it was known long back in 1780 AD. So it is sometimes it is called as contactless electrochemical forming process, because there is a tool actually does not touch to the workpiece surface. So this cathode or tool here, it does not touch to the workpiece surface. So that's why it is called contactless process. And forming process, because this workpiece actually takes the shape of the shape of the tool. Okay, so whatever shape of the tool, shape of the workpiece you want to generate, so you have to make a prototype into that tool, so that the shape of the tool will be made into the workpiece surface. So electrical energy is used to produce the chemical reaction. Works on the Faraday's laws of electrolysis. So here electrical energy is used to produce the chemical reaction here in the electrolyte. So here small DC potential 5 to 25 volt is applied, but here current density is very high, because in ECM process it depends on its main main thing is that you have to apply huge amount of current density. So material removal rate mostly depends on the current density here. So small DC potential 5 to 25 volt is applied across the two electrodes, and these two electrodes actually cathode and anode, it is immersed into the electrolyte. So here in this figure you can see this is the tool here, it is the cathode. So this feed is given to the cathode vertically in the downward direction, and material is removed from the workpiece, which is anode here. So it is connected to the positive terminal and cathode is connected to the negative terminal. Here you can see 5 to 20 volt potential is applied. So flow of electrons here, so this is the flow of electron here in this direction. So transfer of electrons between the ions and electrodes. So whatever electrons are supplied, so these electrons from the DC battery, okay, these transfers of electrons between the ions and electrodes completes the electrical circuit. So here you can see this is the solution, water solution. So whatever electron is supplied from the power supply, DC power supply, okay, so these electrons actually reacts with the hydrogen H2O or water molecule and generates hydrogen gas at the cathode, and also it generates hydroxyl ion in the electrolyte. So you can see here whatever electrons is flowing to the cathode, it reacts with the water molecule and it generates hydrogen gas. So our hydrogen gas is evolved at the cathode here, and at the same time hydroxyl ions also generated at the electrolyte. So at the same time whatever these metallic metals are there, metallic ion break loose from the anode or dissociated from the anode, and after releasing electron to the anode, it comes to the electrolyte. So you can see here, so if it is a iron, the workpiece material is iron, so here, so this Fe2 plus, actually this iron molecule atoms, actually it will release the electrons to the anode, and it will come as a ferrous ion Fe2 plus here. Okay, so this second equation, second reaction. So Fe2 plus, and this Fe2 plus, it will react with the hydroxyl molecule present in the electrolyte, and it will generate ferrous hydroxide. So this ferrous hydroxide, it is insoluble in water. So sometimes this ferrous hydroxide also it reacts with the water molecule and oxygen present in the electrolyte, and it will become ferric hydroxide also. So this ferrous hydroxide with water molecule and oxygen, it will react, and sometimes it will become ferric hydroxide also. Because iron has two valency, 2 and 3, so it may generate ferrous hydroxide or it may generate ferric hydroxide also. So these hydroxyl molecules here, these are insoluble and it will precipitate there in the inter-electrode gap. So you have to flow the electrolyte with a high pressure and high velocity, so that whatever these debris particles are there, whatever these hydroxyl ions, whatever hydroxyl compounds are generated, or metal hydroxides are generated, it has to be actually thrown out from the inter-electrode gap. Also it will throw out the hydrogen molecules, hydrogen gas which is generated at the inter-electrode gap at the cathode. So that phase flow of electron from the cathode should come, and from the anode this electron will come back to the power supply. So this transfer of electrons between the ions and electrodes completes the electrical circuit here. So metal detached atom by atom from the anode surface and appears in the electrolyte as the positive ions, and detached metal appears as the precipitated solid or metal hydroxide. Here you can see M, these are the metal ions. After releasing electron into the anode, it comes into the electrolyte. So it is dissociated, these metallic ions are dissociated from the workpiece. So electrolyte flow velocity, you have to maintain 20 to 30 meter per second. Also you have to flow with a volumetric flow rate has to be maintained 2 to 35 kg per centimeter, so that this whatever this hydrogen gas bubble and hydroxyl metal hydroxide is generated, so it has to be removed from the inter-electrode gap. So these hydrogens are generated at the cathode only, not at the anode. So these hydrogen gas bubbles are generated at the cathode. So application of DC results in the redox reaction. So reduction reaction occurs at the cathode and oxidation reaction occurs at the anode. So if we apply DC voltage, then only this redox reactions occurs. And if we apply only that AC current, then it will leads to a conduction only, because at the first half whatever the situation is there, so electrodes changes their polarity in the first half, and because that is a sinusoidal profile of that AC current, so electrodes change their polarities very fast. So at the first half, whatever electrode polarities are there, at the second cycle electrode polarity will change. So electrode reaction occurs at the first half is reversed in the latter half of the cycle. Okay. So if we reduce the inter-electrode gap between this inter-electrode means gap between this cathode and anode. So this is called this inter-electrode gap, IEG, inter-electrode gap. So if we reduce the inter-electrode gap, that is Y, gap between this inter-electrode, current density, current flow will increase, because if we increase the gap, decrease the gap, in that case your Y decreases, and your resistance actually also decreases, as the resistance is Py by A. So if we reduce the Y, your resistance, gap resistance in between this cathode and anode actually reduces, and in that case material removal rate also increases. So material removal rate will be higher where your gap distance is very less. So high current density as small as high current density in small inter-electrode gap as small as 0.5 millimeter or less promotes the rapid generation of these reaction products. So I told that these reaction products are actually gas bubbles and also this metallic hydroxide. If we decrease the inter-electrode gap, there is a huge generation of these reaction products will be there. And hydroxide solids and gas bubbles act as a barrier. So these hydroxyl metallic hydroxide and gas bubbles, it will make a barrier to the flow of current, to the flow of electrolyzing current. So you have to remove this debris from the inter-electrode gap for the current to flow, for the fresh reaction to take place. So supply of electron at 2 to 35 kg per centimeter square pressure, which lead to the electrolytic flow velocity of 20 to 30 meter per second. So what kind of electrodes are used? You can use acidic electrolyte, you can use the basic salts dissolved in water, acid or basic salts dissolved in water as a electrolyte. So what are the different functions of electrolyte? So now you can see the function of electrolyte is to remove the debris from the inter-electrode gap for the fresh machining to take place, for the current to flow through the inter-electrode gap. Also, whatever the temperature is generated in between this inter-electrode gap, that much heat is actually removed from the inter-electrode gap. Whatever heat is generated, that much heat is actually removed from the inter-electrode gap. So it dilutes the reaction products in between the inter-electrode gap, removes the debris from the inter-electrode gap, dissipate heat at a faster rate, and limits the concentration of ions at electrode surface. So whatever, if it is not electrolyte, if it is not flown, so there is a concentration of ions at the electrode surface, so it will increase. So as the electrolyte is flown, by doing all these actions, with the flow of electrolyte, your machining rate will also increase. So this electrolyte flow velocity, it is determined by based upon the desired flow velocity of the electrolyte, inter-electrode gap, size of the component being machined. And electrolyte properties: consumption, concentration, pH value, temperature, concentration of foreign elements. Okay, so you have to control the electrolyte properties. So its composition, its concentration, its pH value, temperature, and concentration of foreign elements, what about this metal hydroxide, you have to control. So because temperature actually changes the electrical conductivity of the electrolyte, so machining rate will also change. if this concentration of electrolyte increases or whatever is vaporized, in that case electrical conductivity of electrolyte will increase. So in that case your machining rate will increase. So if you want a constant machining rate, uniform machining rate, so you have to maintain the concentration of electrolyte, temperature of electrolyte. So electrolyte properties, tool shape are determined by the anode profile and should be closely controlled. So amount of hydroxide in the electrolyte confined by the continuous removal using the settling tank, filters and centrifuging pump. So this whatever metallic hydroxides are generated, that has to be filtered out from the electrolyte. So concentration, composition and pH value of the solution, electrolyte solution, controlled by adding water. Suppose this concentration changes, so you can remodify the concentration of this electrolyte by adding salt or salt solution or adding water based on the need. So temperature also governs the electrical properties of the electrolyte. So it's already I told that electrical conductivity of the electrolyte changes by changing the temperature. So this temperature should be controlled within plus minus 1 degree centigrade by heating or cooling the electrolyte in the tank. So to maintain the constant material removal rate, spacing between the electrodes should be maintained, and cathode. So to maintain the spacing between the electrode, so cathode is moves towards the anode at the same rate at which the machining from the workpiece actually maintained. Okay, so spacing between the electrodes should be maintained constant. Cathode move towards the anode at the same rate at which work is being dissolved. Smaller inter-electrode gap result in high current density, it will result in high material removal rate. So selection of electrolyte, it should be inexpensive, easily available and commonly used electrolyte is sodium chloride. So now we can see here, so this is the tool here and this is the workpiece. So this tool profile has to be generated into the workpiece surface. Now we can see in this zone current density is maximum. So here also you can see this current density will be maximum entered in the entire zone of the tool where it is interacting into the workpiece surface. So as the current density is maximum here, so machining rate will be higher in this zone and also material removal rate will be higher in this zone. So initially in this zone will be machined and after that this zone will be machined. After that rest of the portion will be machined. Okay. So after some time you will see that this tool and this is the workpiece here. So this workpiece will take the shape of the tool and which is to be generated into the workpiece. So after some time it will take the shape of the workpiece. The shape of the workpiece will form according to the shape of the tool which is used for this machining. So now this main controlling factor you can see here, this is the current density and shape of the cathode or shape of the tool. These are the main two controlling factors for anode profile. So these are the various operations can be done by electrochemical machining process. There are so many things, so many machining operations can be done by this electrochemical machining process, like electrochemical boring operation. You can make a bore hole into that workpiece by using electrochemical machining. Electrochemical broaching operation, electrochemical balizing operation, electrochemical drilling, you can make holes, small holes by using electrochemical machining process, electrochemical deburring operation. So if some bars are actually generated by conventional machining process, these bars can be removed by electrochemical deburring operation, electrochemical die sinking operation, electrochemical grinding operation, electrochemical honing operation, electrochemical machining operation and electrochemical micro machining operation. You can do the micro machining operations also, but in that case you have to change the current and voltage, all these parameters, and you have to vibrate the tool with a very high frequency. So many things you have to change if you use this electrical process for micro machining applications. Electrical milling operation, this is one of another process. Electrochemical sewing, electrochemical turning, electrochemical trepanning operation, electrochemical wire cutting operation, electrochemical drilling operation, shape tube electrochemical machining for high aspect ratio holes. So these are the various machining operations which are obtained by using electrochemical machining process. So now what are the different components of ECM process? So first component is the power supply of this electrochemical machining process, or power source of the process is the first element. Then electrolyte supply and cleaning system is the second element of this process. Tool and tool workpiece, tool feed system is the third component of the process. And workpiece and work holding device system is the fourth component of the process. Now we shall discuss one by one different elements of the process. So here this is the schematic diagram of a electrochemical machining process. Here you can see power supply here. So this is the main switch. This is the power supply here. So current is applied. So this is the tool here. So it is connected to the negative terminal or cathode, and this is our workpiece here. It is connected to the positive terminal. Now this tool is actually fed towards the workpiece by a feeding mechanism. Now this is the motor and this is the pump here. So electrolyte is flown into this perspex chamber by this tubing system. Now it is coming back to this filtering system. So power source, we need a DC power DC current. Amount of voltage is 5 to 25 volt, but amount of current is as high as 40,000 ampere is required, with electrical potential of low value of 5 to 25 volt of electrical potential across the entire cathode gap. So highest current density which is achieved so far is 20,000 ampere per meter square, per centimeter square. So this three-phase AC is converted into the DC power supply to the low voltage high current DC using a rectifier and transformer. So silicon control rectifiers used for both rectification and voltage regulation. Because of their rapid response to changes in process load and their compactness, so voltage regulation of plus minus 1% adequate for most of the precise ACM works. So sometimes there is spark between the tool and workpiece, because due to the lack of process control, equipment failure and operator's error. Electrical circuitry detects these events if there is a short circuit. So electrical circuit will detect these events, and power is cut off using silicon control resistor within 10 microseconds to prevent severe damage to the work and tool. So electrolyte supply and cleaning system consists of pump, filters, piping, control valves, heating, cooling, pressure gauge, storage tank. So this electrolyte has to be flown to the electrolyte chamber, then it is taken away from the chamber by electrolytic flowing system. A smaller gap less than 1 millimeter for achieving high material removal rate is required. Electrolyte cleanliness required to maintain smooth flow of electrolyte and to avoid blockade of inter-electrode gap particles carried by electrolyte. So, electrolyte cleanliness normally done with the help of filters made of stainless steel monel or any other anti-corrosive material. So, filters are periodically cleaned for their proper functioning. So, filters can be placed in a supply pipe just prior to the work closure to achieve good results. This piping system should not introduce any foreign materials like corroded particles, scale or pieces of broken seal material. Also, piping system made of stainless steel, glass fiber, reinforced plastics, plastic lined mild steel or similar other anti-corrosive materials are used for piping and anti-corrosive for piping system. So, piping systems are made of silicon, stainless steel, glass fiber, reinforced plastic, plastic lined mild steel, similar other non-corrosive materials are used for piping system. For metallic piping, metallic parts should be earthed to prevent the anodic corrosion. The stable and fixtures should be insulated from the anode. So, minimum capacity of this electrolyte tank is 500 gallons for each 10,000 ampere of current. So, these reaction products from the electrolyte are separated by natural sedimentation in the first component. Then electrolyte is made go to this component 2, compartment 2 by a filter, then to the last component by a passage between the compartment 2 and 3. Further, it is cleared by a filter attached to the exit port of the tank. So, you can see here this is the container here used for filtering purpose. So, in the first container actually it is electrolyte is coming from the machining zone. So, whatever this electrolyte is there, it is allowed to precipitate there. Then from first to second chamber, there is a filter is placed here. Now, from this second to third component, it will go through another filter, and at the exit of this filter, it will go to the pipe connecting to the electrolytic chamber. So, electrolyte cleanliness required to maintain the smooth flow of electrolyte to avoid blockade of inter-electrode gap by particles carried by electrolyte. So, electrolyte cleanliness normally done with the help of a filters made of stainless steel or any other anti-corrosive material. Filters periodically cleaned for their proper functioning. Filters can be placed in the supply pipe just prior to the work enclosure to achieve good results. Piping system should not introduce any foreign materials like corroded particles, scales, pieces of broken seals. Piping systems are made of stainless steel, glass fiber reinforced plastics, plastic lined mild steel or similar other anti-corrosive materials. For metallic piping, metallic parts should be earthed to prevent any anodic corrosion. So, any metallic part, it should be earthed. Table and fixture should be insulated from the anode. So, minimum capacity of electrolyte is 500 gallons for each 1000 ampere of current. So, single tank system is not recommended because of loss of time and wastage of electrolyte during the draining, cleaning or mixing or filling of new electrolyte in the tank. So, it results in higher cost and 4 accuracy of electrochemical machine components and 4 control of operating conditions. Concrete tank or swimming pool type of tank are pleaded because of their low cost, easy maintenance and reliability. So tool and tool feed system, tool is fed towards the workpiece because material removal at the anodic resolution due to the anodic resolution of the material. So you have to feed the tool towards the workpiece. At the same rate, this anodic resolution is going on. So tools and fixtures should be made of anti-corrosive material. These tools should be made of anti-corrosive material to work for a long period of time in corrosive environment of electrolyte. Tool material should have high thermal conductivity, high electrical conductivity, easy machinability, and dimensional accuracy and surface finish of work. So directly accept workpiece accuracy and surface finish. Tool materials, very soft materials are used for this tool in ECM because there is no wear out of the tool material. So aluminum, brass, bronze, copper, carbon, stainless steel, monel, these are the materials which are used as the tool material. Insulation of tool is required. So those areas of the tool where ECM action is not required are insulated. So lack of insulation on the sides of the die sinking tool causes unwanted machining of the work, results in the loss of accuracy of the machine workpiece, but which type of tool can be recommended? Either these tools may be coated to remove the unwanted metallic resolution at the side of the workpiece. So all these tools should be coated, or you can do one thing, you can use a bead type tool. So fixture should be non-corrosive, also it should be electrically non-conducting materials. Fixture also it should be electrically non-conducting materials. And fixture and tool should be rigid enough so that it will not vibrate due to the deflection under high hydraulic forces of the electrolyte. So it should not vibrate, tool should not vibrate during electrolyte flow. So it should be rigid enough. So you can see that this is the bare tool, this is the coated tool here, coated outside. So this is the bead type tool here. So this is the perspex body. Here a through hole is there. Through this hole, actually this wire is coming inside at the bottom surface of the bead. So there are different zones are there. So this is the stagnation zone 5. Then 6 is the front zone. 7 is the transition zone. 6 is the front zone, 7 is the transition zone, 8 is the side zone, 9 is the tapered side, and 10 is the tool bit. So here you can see this is the bit type metallic tool is attached. So this is non-conducting material, this is the conducting material, it is attached to this non-conducting material by using this kind of thread here. Okay. So as this portion is made of perspex, so it is made there is a hole is made inside that perspex, and this titanium electrode is inserted and it will touch to the drill bit. So workpiece and work holding system, only electrically conducting workpiece materials can be machined. The chemical properties of the anode material largely governed by the material removal rate. So work holding devices made of electrically non-conducting materials having good thermal stability, low moisture, absorption properties, graphite fiber, reinforced plastics, perspex. These are actually used for workpiece and work holding system. So what are the advantages are there? So it can machine only highly complicated and carved shapes in a single pass. Tool life in ECM is very high because there is no tool here, practically there is no tool here. So single tool to machine large number of workpiece. Machinability of workpiece material independent of their physical and mechanical properties. It does not depend on the physical and mechanical properties of the workpiece material. So low scrap rate, reduce inventory expenses, almost automatic operations, and low overall machining time. Can machine only electrically conducting workpiece material. These are the disadvantages. Few limitations are there for this same process. It can work on the electrically conducting material. For electrically non-conducting material, this process is not suitable. So this machine component accuracy depends on the tool design, degree of the process control imposed, and complexity in the shapes of the shapes produced. So machining of materials consists of hard spots, inclusions, sand and scale that are present in the some practical difficulties. Under certain circumstances, incapable of economically producing dimensional tolerances desired on the workpiece, cannot produce sharp corners and edges, not environmental friendly. Because of this, chemicals are used, so it is not economically friendly. Also can produce sharp corners and edges in case of electrochemical machining process. So what are the applications of ECM process? So it is used for machining very hard materials, high strength temperature resistant materials. Also it is used for measuring very complex contours on the workpiece surface. So which is not possible for conventional machining process. So machining of hard and tough materials, especially with complex contours. ECM is used for turning, trepanning, broaching operations, grinding operation, for fine, hole drilling operation, die sinking operation, piercing operation, deburring operation, and plunge cutting operation. So these are the so many operations can be done by this ECM process. So it is widely used in industries. Commercial machines are available in industry. So it is used in aeronautics, nuclear technology, space vehicles, automobiles and turbines. These are the industries where these ECM machines are extensively used. So typical ECM applications are, it is used for machining of turbine blades, which is made of high strength temperature resistance material. So you can see that in the turbine blades, so many complex surfaces are there on the turbine blades. How to machine by normal conventional machining process. Also these turbine blades are made of these high strength temperature resistant materials. So these turbine blades are actually machined by this ECM process. Coping of internal and external surfaces, cutting of carbon slots, any kind of carbon slots you want to cut. So you have to generate a tool. So whatever surface you want to generate, so you have to generate on the tool. And you can cut the workpiece using the tools. So generally these tools are actually made of very soft material, so you can generate any kind of complex profile on the tool. And something can be replicated into the workpiece surface by electrochemical machining process. So production of long curved profiles you can generate by this ECM process. So any kind of long curved profile you can generate. Machining of gears, production of integrated blade nozzles in diesel locomotives, production of connecting rods, machining of thin, large diameter diaphragms. These are the some applications of electrochemical machining process. So now, what will be the mechanical properties for this ECM process? Now in conventional machining process, you know there is a compressive residual stress is generated. So because of this compressive residual stress, this fatigue life of the workpiece is increased. Okay. So in ECM process, there is no hydrogen bubbles are generated. So there may be chances of hydrogen embrittlement into the workpiece surface. But you can see, we have discussed that hydrogen gas is generated in the cathode, into the cathode surface. So it is not generated into the anode surface. So anode actually basically it is used as workpiece. So as it is not generated into the anode, so there is no chance of hydrogen embrittlement into the workpiece. So no effect of ductility, yield strength, tensile strength, ultimate tensile strength, micro hardness. These things does not change in ECM process. These are these mechanical properties like ductility, yield strength, ultimate tensile strength, micro hardness. These things does not change into the workpiece surface. Surface layers damaged during conventional machining process can be removed. So what about the surface layers? I told that these compressive residual stress are generated. So this in conventional machining process, because of this compressive residual stress, this outer layer become very harder. Okay. So what about this surface layer damaged during this conventional machining process can be removed by ECM process. Also suppose in EDM process there is a brittle material. What about this molten material? It is redeposited there. So this redeposited material, it is very hard. Okay. So also in EDM process, it changes the property of this material. So this material can be removed. What about this property, material property, whatever this material property changes, that layer also, recast layer also can be removed by this EDM process, by this electrochemical machining process. So surface layers damaged during conventional machining can be removed by this ECM process. So improvement in properties of this work material. So reduces fatigue strength of the conventional machining component having compressive residual stress. So as the compressive residual stress is not generated in ECM process, which is generated in EDM process, in conventional machining process, so machine parts produced by ECM process and machine parts produced by conventional machining process. In conventional machining process, this fatigue life is more than ECM process. So in ECM machine surface has better wear, friction and better corrosion resistance properties. Now this ECM process works on the Faraday's laws of electrolysis. So what is the Faraday's laws of electrolysis? So amount of material removed from the workpiece depends on the quantity of electrolyte, quantity of current flowing through the workpiece. So this amount of chemical change produced by an electric current. So amount of chemical change produced into the workpiece surface by an electric current, or the amount of substance deposited or dissolved. In our ECM process, the amount of material is dissolved is proportional to the quantity of electricity passed through the material. So amount of material dissolved or deposited is proportional to the quantity of electricity passes through the workpiece. Okay. So this mass, if you consider this mass, this amount of material dissolved due to the ECM process, if it is M is proportional to I into T. I is the current, T is the time. So it is proportional to the I into T. Now this Faraday's second law tells that the amount of different substance deposited or dissolved, suppose substance A and substance B, into substance, if you flow same amount of current to these two different substances, amount of material dissolved from the workpiece will be different. It depends on the electrochemical equivalent weight of the material. So this amount of different substance deposited or dissolved by the same quantity of electricity are proportional to their electrochemical equivalent weight, or M proportional to E. E is the electrochemical equivalent weight. And also from the first law, M is proportional to I into T. I into T is the quantity of the current electricity flowing the workpiece. Okay. So now we can write M proportional to I into T into E. Now M equal to IT into E by F. F is the Faraday's constant. So its value is 96,500 ampere second. So if you write in terms of material removal rate, G M R R G M dot, or M dot, so you can write it is IE by F. So M by T will come, so M by T will give the M dot equal to metal MRRG, metal removal rate in gram per second, it will give IE by F. So here I is the ampere current, T is the second current flowing through the workpiece, E is the gram equivalent weight. So E can be represented as A by Z. A is the atomic weight, Z is the valency here, and F is the Faraday's constant, which will give 96,500 ampere second, and M is the mass in grams. So now this Faraday's law does not consider few things like change in valency during electrochemical dissolution. Suppose iron you are machining, so iron has two valency, valency 2 and valency 3. So while generating this metallic hydroxide, it will be ferric hydroxide or ferrous hydroxide. So what will be the valency of these metallic ions while dissolution? So it does not tell about that. So change in valency during electrochemical dissolution, it does not account for this. Also it does not account for gas evolution and bubble formation. So gas also evolved, hydrogen gas has evolved at the cathode, also oxygen gas and bubbles also generated during ECM process. Because of that, electrolytes, electrical conductivity also reduces. When hydrogen gas evolved, electrical conductivity of this electrolyte reduces or changes, and there is a change in temperature also of this electrolyte. Because of this increase in temperature of this electrolyte's electrical conductivity increases along the electrolyte flow path. Okay. So that's why this K electrolyte's electrical conductivity changes. So material removal rate also changes. So, but this Faraday's law actually does not account for these things. So there is a change, presence of passivation layer. So formation of this protective film on the workpiece surface. Because of this passivation layer, this metal hydroxide, it is deposited on the workpiece surface. Also there is a passivation layers are generated on the workpiece surface. So it depends on the chemical and electrochemical behavior of the material. So this passivation layer has to be removed for machining to takes place. So this Faraday's laws also does not account of this passivation layer on the anode surface. Now we already told that it does not account for the valency at which it is actually this metal is dissolved. And also for this, for machining of alloy, where there is a mixture of different metals are there. Suppose you are doing electrochemical machining of an alloy which consists of n number of metals. So how to calculate the electrochemical equivalent weight of the metal, of the alloy, electrochemical equivalent weight of the alloy. So there are two processes are there. which take care of the electrochemical equivalent weight of the alloy. So first one method is the percentage by weight method, and second one is the superposition of the charge method. So this percentage of weight method, so here this E equal to A by Z A, it is calculated by multiplying individual electrochemical equivalent weight multiplied by their percentage, weight percentage, multiplied by their respective properties by weight xi, and then summing them up as shown in this equation. So here A by Z is the electrochemical equivalent weight of this alloy element, and here individual electrochemical equivalent weight Ai by Zi multiplied by this their percentage, weight percentage, and it is summed up for all the elements I equal to 1 to n here and divided by 100 here, and after simplification it will give the electrochemical equivalent weight of the alloy. So n is the number of constituent elements in the alloy. And the second method is the superposition of the charge. So now total electric charge required for dissolution of 1 gram of this alloy is Z by A into F. So total electric charge required to dissolve 1 gram of alloy is Z by A of the alloy multiplied by F. This much coulomb of charge is required. Now it is equal to the electrical charge required for individual element to dissolve their individual mass contribution. So now here Z by A into F, it is the charge required for 1 gram of alloy. Now here Zi by Ai multiplied by their weight percentage and divided by 100, and summation I equal to 1 to n will give the charge sum or charge required for individual element multiplied by F will give the sum of charge required for individual element. Now after simplification it will give A by Z equal to 100 by summation I equal to 1 to n xi into Zi by Ai. So electrochemical equivalent weight calculated from both the methods, almost it will give the similar reals, but their reals differs. There is a slight variation in their reals is there. So you can calculate electrochemical equivalent weight of alloy by any one of these two methods. So now how to calculate the volumetric material removal rate by using the electrochemical machining process. So for doing this one, actually there are few assumptions are there. Electrical conductivity of the electrolyte in the inter-electrode gap does not change, so it is constant. Although this electrical conductivity of the electrolyte changes with temperature and changes with the hydrogen gas bubbles, but for the sake of calculation here, for the simplification of the calculation, it is assumed as constant. So K, electrical conductivity of the electrolyte, does not change in the inter-electrode gap. So electrical conductivities of the tool and workpiece is very high. It is around 1 lakh per ohm per centimeter for the tool and workpiece as compared to the electrolyte. So electrolyte, it is 1 ohm, 1 per ohm per centimeter. So in that case, as the electrical conductivity of the electrolyte is very less as compared to the cathode and anode, so this tool and workpiece may be considered as the equipotential. So effective voltage across the electrodes is V minus del V. So del V, V is the applied potential, del V is the potential which is actually used for this tool, which is absorbed in the tool and in other cases. Okay. So this is the total applied voltage V minus del V. So this del V is the over potential here. So also anode dissolves at one fixed valency of dissolution. Although for different materials different valency of dissolution may be there, but here only one valency of the metal actually considered. So here we have considered plain parallel electrodes, and feed is given to the electrode here, normal to the feed direction. So electrolyte is flowing in this direction, normal to the feed direction. So material removal rate, volumetric, this material removal rate gram MRRG we calculated as I by F. Now eta is the current efficiency, means whatever current we are applied, so total current is not used for this material removal rate. So only few percentage of that current is used for this material removal of the workpiece. So that's why there is a current efficiency of eta is considered here. Now to get the volumetric material removal rate, so you have to apply, you have to divide this right hand side by rho, by density of this workpiece material. If you divide that, then it will give the volumetric material removal rate, which is eta I by F into rho A. Rho A is the density of this workpiece material. At equilibrium, feed rate of the tool is equal to the dissolution rate from the workpiece. So at equilibrium, feed rate F of the tool is equal to the rate at which the thickness of the anode being reduced. So at equilibrium rate, this thickness of the anode being reduced, which is the linear material removal rate. Now how to calculate this linear material removal rate? Now this in equation 2, if we divide both sides by cross section area of the common area A, cross section area of the tool, if you divide by that in the both sides, then it will give the linear material removal rate MRRL. So left hand side you divide by A, cross section area of the tool. Right hand side also you divide by cross section area A. So it will give I by A equal to J here. J is the current density. So J eta E F by rho A here, left hand side it will give the linear material removal rate. So this linear material removal rate is nothing but penetration rate or millimeter per second. So eta is the current efficiency here, J is the current density equal to I by A here. I is the current, A is the cross section area, ampere per millimeter square. Rho is the density, gram per millimeter cube, or anode material or workpiece material. So here you can see this is the cathode here, this is the anode. Electrolyte is flowing in this direction from left to right. So distance between this tool and workpiece, this is the Y. Distance between the tool and workpiece, this tool cathode and anode, it is connected to a power supply, DC power supply here. Feed F is given to the cathode towards the anode here, and in Z direction there is no change in the electrolyte. Electrical conductivity, it does not change in the electrical conductivity of the electrolyte. So in the Z direction actually we are not considering, so we are considering only two-dimensional case. So now current density during ECM as a function of shape of the electrode. So now we have to calculate the current density. So it depends on the shape of the electrode. Here plane parallel shape of the electrodes we have considered, work and tool, and the distance between these two electrodes, this is Y, and voltage applied across them, it is V minus del V. V is the applied voltage, V and del V is the work potential. So total voltage applied is V minus del V, and electrical conductivity of the electrolyte. So J can be represented as a V minus del V into K by Y. Y is the gap, inter-electrode gap, K is the electrical conductivity of this electrolyte, and V minus del V is the total applied voltage. So V minus del V by Y is the potential gradient in inter-electrode gap. Now linear MRRL equal to penetration rate or rate of change of inter-electrode or MRRL, you can write this one as penetration rate or rate of change of this inter-electrode gap, or you can write this one as dy dt. So here in this equation you can write MRRL equal to dy by dt, this one minus f. So you can write this one as dy dt equal to j, this is the linear material removal rate, MRRL, you can write as dy dt, right hand side it is j e eta f into rho a. So it is already there, j e eta f into rho a here. Okay. Now during ECM, tool is moved towards the workpiece at a rate of f millimeter units per second. So now effective rate of change of inter-electrode gap is given by dy dt equal to j e eta f rho a minus f. Now for equilibrium condition dy dt equal to 0. So dy dt will be 0. Now so you can write for equilibrium condition j e eta by f rho a minus f equal to 0 here. Okay, because dy dt there is no change in inter-electrode gap for equilibrium condition. So now you can put it as a 0 here. So you can write this one as dy dt equal to 0, or it will become j e eta by f rho a equal to f equal to feed rate. J now you put it as v minus del v into k by y, v minus del v into k into y, ye is the equilibrium gap. Now you put it here, this eta e eta by f rho a equal to f. Now after simplification you will get this equilibrium gap. So this is the y is the equilibrium gap in between this tool and workpiece. So equilibrium inter-electrode gap y can be achieved provided f and v are constant, feed rate and voltage are constant throughout the machining. Throughout machining, feed voltage are constant throughout the machining. So y can be calculated as v minus del v into k e into eta by f into f rho a. So from this equation you can calculate this equilibrium gap. Now inter-electrode gap in ECM. So similar equation I can write it here, dy dt equal to e v minus del v into k by f rho a into y minus f here. So now in equilibrium condition this dy dt will attain a value of 0. So now this e v minus del v into k by f into rho a can be considered as a constant. It can be considered as a constant. So dy dt we can write as dy dt equal to c by y, constant, machining constant by y minus f. C is the machining constant here. Constant for a particular work and electrolyte combination only if v minus del v and k remain constant during the process. We have considered this. Total applied voltage, applied potential is constant, and also electrolyte electrical conductivity is constant in between these two electrodes. So now we can write this one, this dy dt equal to c by y minus f. So now there are two conditions are there. One is finite feed rate and another one is the zero feed rate. So now your machining is going on. So you can give a feed to the tool with the finite feed rate, or you can keep fixed. This tool may be kept fixed, or f equal to 0, feed equal to 0, feed of the tool is 0, or you can give a finite feed rate towards the tool. So in actual practice, two cases are there: zero feed rate f equal to 0, and finite feed rate f not equal to 0. So in case of zero feed rate, so in that case dy dt equal to c by y, because f equal to 0 here. So dy dt equal to c by y, zero feed rate, or y dy equal to c dt. Now if we integrate this one, in both sides, it will become y square by 2. So 2 Ct, here Ct, C into T, 2 Ct plus K. K is the constant of integration. Now if we put at t equal to 0, that is the interelectrode gap of y0. So at t equal to 0, that is interelectrode gap of y equal to y0. Now if you put in this equation here, so k equal to y0 square, k equal to y0 square. Now put this k equal to y0 square here. Now we will get y equal to root over 2ct plus y0 square. So root over of this 2ct plus y0 square. So this is the interelectrode gap for a 0 feed rate. So now if you plot this one for t equal to 0 here, that is interelectrode gap was y0. Now with time, if we increase the time, this interelectrode gap will increase. Means if we increase the time to a infinite value, this interelectrode gap will also increase. So this is not the practical case. If we increase the time, after some time this interelectrode gap will increase if we don't give any feed, and after that this machining will stop, because this machining will start when a minimum interelectrode gap is maintained. Now for the finite feed rate, what will be the y? What is the value of y for the final feed rate or feed f not equal to 0? For f not equal to 0, IEG at the equilibrium condition will remain constant. Interelectrode gap for the equilibrium condition will become constant, or dy dt equal to 0. So if we put dy dt equal to 0, y equal to ye. So in this equation, if we put dy dt equal to 0, so here y equal to ye equal to c by f. So in this equation, y equal to CF, C by F. So here if we put dy dt equal to 0 for the equilibrium condition, so if we give a finite feed rate f not equal to 0, interelectrode gap at the equilibrium condition will remain constant, or dy dt will become 0, or y equal to ye equal to C by F. Interelectrode gap always tends to attain a equilibrium value during electrochemical machining process. So interelectrode gap always tends to attain a equilibrium value during electrochemical machining process. For making generalized analysis, some parameters are made dimensionless. Okay. So now y is made dimensionless. So non-dimensionalization is done. Y dash equal to y by interelectrode gap by equilibrium interelectrode gap. So now y already we have calculated here equal to C by F. So now put this y value equal to C by F. Now it will become yf by C. Now time also non-dimensionalized, like this, t dash equal to t by y by f. So here it means how much time is required to machine interelectrode gap. So equal to t dash equal to t by ye by f. T by ye already we know this c by f. So it will become t into f square by c. Now y dash equal to here yf by c. Now we can get this y equal to cy dash by f here. Now t equal to t dash equal to t into f square by c. Now we will get t equal to Ct dash by f square. Now put this value of this y and t into this equation. So dy dt equal to c by f, c by y minus f. Now put this d y equal to cy dash by f, and this d t equal to you put Ct dash by f square equal to c by f, c by y. Now y equal to cy dash by f minus f. Now it will come in this form, dy dash by dt dash equal to 1 by y dash minus y minus 1. Now put it in this form, 1 minus y dash minus y. So dt dash by dy dash equal to y dash by 1 minus y dash. Now dt dash equal to y dash by 1 minus y dash into dy dash. Now dt dash equal to minus 1 plus y dash plus 1 by 1 minus y dash into dy dash. Now integrate in both the sides, you integrate. Now it will become t dash. This one it will become minus y dash. Then this one 1 by 1 minus y dash, it will become ln y dash minus 1 plus k. K is the integration constant. So it can be calculated as putting the initial value at t dash equal to 0, y dash equal to y0 dash. Now we put this value here. Now we will get the value of k as y0 dash plus ln y0 dash minus 1 here. Now put this value of k here in this equation. So now we will get this t dash equal to minus y dash minus ln y dash minus 1 plus y0 dash plus ln y0 dash minus 1. So now t dash will get this y0 dash minus y dash plus ln y0 dash minus 1 by y dash minus 1. So this is the equation for this t dash. So t dash you can calculate. So y0 dash minus y dash plus ln y0 dash minus 1 y dash minus 1. Now equation 6, only positive values of y dash are possible, because if you put y dash equal to 0, this means that it implies that a short circuit between the tool and workpiece is there. So only positive values of y dash you can put here in this equation. So solution of this equation dy dt equal to c by y minus a for non-zero f or finite feed rate without any non-dimensionalization, you will get in this form. So t equal to 1 by f y0 minus yt plus ye ln y0 minus ye by yt minus ye. So yt is the gap in time t. So you can calculate this t dash by non-dimensionalization, or without non-dimensionalization you can calculate this t. So now if we plot this y dash here, so y dash is plotted, and here y axis it is y dash equal to fy by c, x axis it is plotted t dash. Now we can see whatever value of this y0 initial value, whatever initial value you take, initial inter-electrode gap. So here in this case, if it is 5, it is initial inter-electrode gap is 4, 3, 2, 1.5, 0. So in both the cases, in all the cases, you will see it will asymptote to a value of y dash equal to 1. So y dash equal to 1 means, here if you put y dash equal to 1 means y equal to ye. So it will reach to the equilibrium gap. So it will reach to the, this inter-electrode gap will reach the equilibrium gap. So y dash is asymptotic to y dash equal to 1, or linear material removal rate is equal to the feed rate, or y equal to ye. So whatever value of initial inter-electrode gap you will take, so linear material removal rate will take the value of this linear feed rate, or y inter-electrode gap will achieve the equilibrium inter-electrode gap. So this is called self-regulating characteristics of ECM process. There are three cases are there. When feed rate is equal to the linear material removal rate, when feed rate is greater than linear material removal rate, and when feed rate is less than linear material removal rate. So in the first case, when feed rate is equal to the linear material removal rate, in that case stable machining will take place, and in that case inter-electrode gap is equal to the equilibrium gap. And in the second case, when feed rate is less than linear material removal rate, in that case we are not giving at the same feed with the machining, or machining is going on from the workpiece. So you are giving less feed. So in that case, what will happen? Gap between this tool and workpiece will increase. If gap between tool and workpiece increases, then current density will decrease. If current density decreases, then machining rate will decrease or material removal rate will decrease. So if material removal rate decreases, means gap between the difference between the linear material removal rate and feed rate will decrease, or ultimately it will take the shape, it will take linear material removal rate will take the value of feed rate. So here it is written, initially interelectrode gap will increase and attain a value of greater than equilibrium gap, or Y is greater than equilibrium gap. Current density will decrease as compared to the current density at the equilibrium interelectrode gap, and that's why material removal rate will also decrease. And if this material removal rate decreases, the difference between the feed rate and the linear material removal rate will decrease. So if this gap between this difference between the feed rate and linear material rate decreases, interelectrode gap will start decreasing and will attain a equilibrium gap, or MRRL will become a equilibrium gap equal to F. And if feed rate is greater than, in the third case, if feed rate is greater than material removal rate, initially this gap will become more than the equilibrium gap. So if gap between is becoming more than the equilibrium gap, equilibrium interelectrode gap, your current density will increase. If current density increases, more material removal will be there. If more material removal is there, this difference between the linear material removal rate and F will decrease, and ultimately it will take the equal to the feed rate. Or initially this gap will be smaller than the equilibrium gap, YE, Y less than equilibrium gap. Current density will increase as the gap reduces, as compared to the situation when Y equal to gap, interelectrode gap is equilibrium gap. So that's why if current density increases, your material removal rate will increase, and difference between the F feed rate and linear material removal will become small, and that's why gap will tend to attain the equilibrium gap, or linear material removal rate will become F. So this is the self-regulating characteristics of ECM process. So now generalized equation for this interelectrode gap, for dy by dt equal to C by Y minus F. In that equation, for F equal to 0, we have seen that if we increase the T for infinite value of T, that is infinite value, so this interelectrode gap also increases infinitely, non-linearly. So it is not the case. So it is not the practical case. Practically, actually, this linear, if we increase the time, over time, and with a zero feed rate, after some time, it will become this interelectrode gap will increase. After some time, this machining rate will stop. Machining will stop. There will not be any electrochemical machining, because minimum interelectrode gap should be maintained for the machining to take place. And for the second case, this T dash, this non-dimensional case, when if there is a finite feed rate is there, so this is the implicit form of the equation. To solve this implicit form, we have to take help of the numerical analysis, and you have to take help of the finite difference method, or finite element method, or boundary element method. So in the equation, in the first equation, when F equal to 0, this Y equal to root over 2ct plus Y0 square. So it predicts an infinite value of Y as T approaches infinity. As the gap increases, current density will reduce, and hence material removal rate gradually diminishes, and very large value of gap this process would come to a standstill, not well reflected in equation 5. Now, for the second case, when f equal to 0, in that case, it is a implicit form of the equation. It is solved iteratively, and it consumes lot of computer time, and this solution is a bit of tedious. So that's why a single equation is derived, conveniently used in FEM, a finite difference method and bounded element method, which is derived by Jain et al., Jain and Pandey, which is applicable to both f equal to 0 feed rate and finite feed rate. So now we can write this one dy dt equal to j e eta by f into rho a minus f. Then dy dt equal to, we can write in this form j e eta f rho a minus f multiplied by dt. So in this equation, all factors are actually constant except this j, because E eta, Faraday's constant, rho a, density of this anode, all these are actually constant except this j. So you can write all factors are constant except this j. So in FEM, finite element method, bounded element method, finite difference method, this element size is very small. So in that very small element size, you can consider this current density is constant. So within that element, you can consider this current density J is assumed to be constant for a time, for a very small time of dt. You can consider. So this was, so now you can write this was dy equal to c minus f. So you can consider this one as a constant for a very small domain and for a very small time. So you can write this one dy equal to c minus f into dt. Now integrate this equation y equal to c minus f into t plus c dash. C dash here actually integration constant. Now for t equal to 0, if we put this initial condition for t equal to 0, y equal to y0. Initial inter-electrode gap is y0. So if you put this one in this equation, then c dash will become y0. Now we put this c dash equal to 0 in this equation. Now we will get this one as y equal to y0 c minus f into del t. So del t, here it is del t is taken because this equation is valid, because this current density is constant for a very small time, del t. So this single equation can be used for both the cases of finite feed rate and zero feed rate. And also it takes very less amount of computational time for solving to calculate the inter-electrode gap between cathode and anode. So now in some cases when feed rate or this cathode and anode, it is inclined to an angle theta to the feed rate. So this is the cathode and this is the anode, it is inclined at an angle theta to the feed rate. So in that case, you have to take the component of the feed, f cos theta instead of f. Okay, so feed rate f is replaced by the component f cos theta. When theta equal to 90 degree, f is normal to the workpiece. When theta equal to 90 degree, then f is normal to the workpiece. So then feed is 0. So condition of f equal to 0 would apply. So in that case, condition of f equal to 0 will apply. Angle theta is measured between the normal to the workpiece. So this is the normal to the workpiece and in between the feed direction. So this is the feed direction, this is the normal to the workpiece, and this is the angle theta. Now how to calculate the maximum permissible feed rate in electrochemical machining process? Now this volumetric material rate can be calculated as EI by eta by 96,500, this is the value of A, Faraday's constant, by rho A. So eta is the current efficiency. So it is almost 100% for a NaCl solution, NaCl as electrolyte. So it is almost 100% for aqueous solution of NaCl as electrolyte. So it is lower than 100% when we will take nitrate or sulfate as the electrolyte, and it is more than 100% when electrically non-conducting inclusions are there in the anode. Suppose this kind of electrically non-conducting inclusions are there. So in that case, this outside these materials will be removed. When this material is removed by ECM process, this one also will be removed automatically. Okay. So it is a electrically non-conducting inclusions are there. So this material is not removed by ECM process because outside materials are removed by ECM process. So this material also it is removed from the workpiece. So in that case, automatically your current efficiency will become more than 100%. So when electrically non-conducting inclusions are there in the anode. Now one concept is that specific material removal rate, that is meter cube per ampere per second. Specific material removal rate can be calculated as volumetric material removal rate by current. MRR V by current I will give the specific material removal rate. MRR V volumetric material removal rate by current will give the specific material removal rate. So in equation 7, if you divide left hand side by MRR V by I, then it will become eta E 96,500 into rho A. Now this feed rate can be written as J into current density into volumetric material removal rate. Now current density we can write as B minus del V into K by Y. We have seen earlier. And now specific material removal rate can be written as eta E by F into rho A. So this is feed rate meter per second. So now we are going to calculate what should be the maximum perceptible feed rate in ECM process. Because if we increase the feed rate, then this gap between this interelectrode gap will decrease. If gap decreases, then current density will increase. If current density increases, then more material removal will be there. So at the same time, huge amount of temperature will be generated. So this temperature is generated, then electrolyte has to be flown away from that gap, whatever, because this temperature will be dissipated to the electrolyte. So this electrolyte has to be removed or flown away from the interelectrode gap. So if it is not removed from the interelectrode gap, what will happen? Electrolyte will boil in between this interelectrode gap, because already we are maintaining very small gap. In that small gap, if we increase the current density, automatically this ohmic heating will be there. Because of this ohmic heating, this electrolyte will boil. So to avoid this boiling of this electrolyte, you have to remove that electrolyte from the interelectrode gap. So electrolyte will carry away the heat from the interelectrode gap. So upper limit of electrolyte flow rate. So there is a upper limit of the electrolyte flow rate may be there for a electrolyte flow system. So which poses a limit to maximum feed rate without permitting the electrolyte to boil. So there are few assumptions are there to derive the maximum permissible feed rate. So electrolyte is allowed to heat up to a boiling temperature. So electrolyte is allowed to heat up to a boiling temperature. So it is not allowed to boil. So up to boiling temperature it is allowed. So from its initial temperature Ti2, it is allowed to up to this boiling temperature. So when only the ohmic heating is significant. Other than ohmic heating, like viscous heating and any other heating is not. So because these electrodes also will become heated up. So this heat due to the from the electrode, so it is not considered because electrode will become heat up. So this heat is actually dissipated into the convected into the electrolyte. So that heat is not considered, only that ohmic heat is considered. So also we have considered this electrolytes electrical conductivity is constant. So K is constant, electrolytes electrical conductivity, it does not change with temperature. So we have considered that thing. So heat generated because from Ti initial temperature, electrolyte from initial temperature to the up to boiling temperature, Me C specific heat, Tb minus T. So heat generated from electrolyte from initial temperature to the boiling temperature. So St. So M E mass of electrolyte, C is the specific heat of that electrolyte, and Tb electrolyte is from initial temperature, it has come to the boiling temperature Tb. So now we can write Me equal to mass of electrolyte as volume of electrolyte multiplied by density of this electrolyte C Tb minus T. Now H0 by T equal to VE by T rho E Ct Tb by Ta. Now power required for the electrolyte, so it should be multiplied by 4.2 to convert it into joule, so 4.18, and Q dot is actually volumetric flow rate of the electrolyte here into rho E C Tb minus Ti. Now power you can convert this one as I square R. I is the maximum permissible current, Im into R. So equal to 4.186 Q dot volumetric flow rate of electrolyte, C is specific heat, rho E is the density of this electrolyte, Tb minus Ti. So Im, after simplification it will take this form, Im equal to 4.186 Q dot rho E C Tb minus Ti into A divided by Y. So here gap resistance is Y by K. Y is the inter-electrode gap, K is the conductivity, A is the cross-sectional area. So R is written as Y by K. So an increase in the I or current density, if we increase the distance, then current density will increase, and it will require increased feed rate. So it will require increased feed rate for machining under equilibrium condition. So maximal permissible feed rate can be calculated as Fm equal to current density into specific material removal rate. So current density already we know Im by A, current by area. Im already we have calculated here. So now put this Im here, and specific material removal rate is eta E into F into rho A. Okay, so now it will take in this shape. So change in temperature is Tb minus Ti for a specific feed. So this is the maximum permissible feed rate which is allowed to avoid electrolyte to boil. So what is the maximum permissible temperature rise, which is Tb minus Ti. Maximal permissible temperature rise of the electrolyte can be calculated from this equation. So here it can be calculated from this equation. So del T equal to 2.23 into 10 to the power 9 Ya by K Q dot rho E C F rho A by eta E. So Y is the inter-electrode gap, A is the cross-sectional area, T is the electrolyte's electrical conductivity, Q dot is the volumetric flow rate of electrolyte, rho is the density of this electrolyte, C is the specific heat of the electrolyte, F is the feed rate, rho is the density of this electrolyte, E is the electrochemical equivalent weight, eta is the current efficiency. So now electrical conductivity of this electrolyte actually increases because of this rises temperature. When temperature rises, electrical conductivity of the electrolyte also increases. Suppose if we consider this NaCl solution, if we increase the temperature from 10 degree to 20 degree, you can see this specific conductivity, electrical conductivity of this electrolyte increases. From 10 degree to 20 degree, 20 to 30 degree and 30 to 40 degree, you can see electrical conductivity of this electrolyte increases. Also initial concentration if we increase, then also electrical conductivity of this electrolyte increases. Same case for this HCl solution also. If we increase the concentration of this electrolyte HCl solution, then your electrical conductivity increases. And also if we increase the temperature of this electrolyte, then also from 5 degree to 65 degree, you can see electrical conductivity of this electrolyte increases. So electrolyte conductivity is a function of temperature of this electrolyte, and also it is a function of presence of bubbles, hydrogen gas, contamination by the sludges. Because sludges are there, this contaminated into the entire electrode gap. So if more sludges are there, electrical conductivity of this electrolyte will change. Presence of bubbles also will reduce the electrical conductivity of the electrolyte. So size and distribution of this hydrogen gas bubble affect the changes in the K if we ignore this oxygen and water vapor and other gas bubbles. If we consider only hydrogen gas bubbles are evolved at the cathode, so it is size, hydrogen gas bubble size and its concentration also affects the changes in K. Temperature increases K electrical conductivity, while hydrogen gas bubble decreases the electrical conductivity of this electrolyte. So gap gets trapped, that is interroad gap varies. So that's why at the downstream direction, so electrolyte is flowing at u0 velocity. At the downstream direction, if you see, this gap, interelectrode gap actually varies. Suppose this is the tool here and this is the workpiece here. So workpiece actually moving towards the tool here. So initially this gap is y0 here. Now you can see this gap actually varies in between this tool and workpiece, because this electrolyte is flowing. So in downstream direction you will see there is the concentration of these hydrogen gas bubbles. So now effect of temperature on electrolytes electrical conductivity. So here for doing this one, heat generated due to the viscous flow of electrolyte over voltage, chemical reactions, heat transferred through the electrodes are negligible. We are not considering heat generated due to the viscous flow of electrolyte, over voltage or chemical reactions, we are not considering here. So heat transferred through the electrodes are also negligible. So now using the conservation of heat temperature gradient along the electrolyte flow path, you can see I square R equal to U is the flow velocity of this electrolyte, rho E C into del T into Y equal to I square R. So here same thing actually we are using. Now we can consider I equal to V minus del V square into K by Y into dx. Now we put R equal to Y by K. So after putting this, it will become in this form dt dx equal to V minus del V square into K U rho E C into Y square. So now V minus del V square U0 rho E C by Y0 square, we can consider this one as a constant. So we can write it A, and here ultimately we can write it A into K. Now K is the electrical conductivity of this electrolyte. Now we can write this one K equal to K0 1 plus alpha T minus T0. So temperature, it rises from initial temperature T0 to certain value of T. So K equal to K0 into 1 plus alpha T minus T0. Alpha is temperature coefficient of specific conductance. It can be written as dk by K0 into dt per degree centigrade. So now after simplification, this equation will come dt by 1 plus alpha T minus T0 equal to AK0 into dx. So now if we if we do the integration here, it will become ln 1 plus alpha T minus T0 alpha K0 a into x. So now T minus T0, you can write this one as 1 by alpha exponential alpha a K0 x minus 1. So now J, current density, you can write as B minus del B into K by Y. So B minus del B by Y, K equal to, we can write 1 plus K0, 1 plus alpha T minus T0. So this is B minus del B by Y, K0, 1 plus alpha T minus T0, you can write as exponential alpha K, K0 x. Okay. So this is the effect. So current density you can write in this form. Okay, so current density will change if we increase the temperature of the electrolyte. So effect of hydrogen gas bubbles on K. So to accurately predict the variation in the intercalated gap along the electrolyte flow path, consider effect of hydrogen gas bubbles, presence of sludge in the K. So quantitative analysis of the effect of sludge on the electrolyte electrical conductivity, there is no reference in the literature. So effect of sludge on K on electrical conductivity of this electrolyte is not considered here. Only that effect of hydrogen gas bubbles on the electrical conductivity of this electrolyte is considered here. So rate of evolution of hydrogen gas bubble at the cathode surface governed by the current density on its surface. Hydrogen gas bubbles are swept away by the flowing electrolyte. So their mass concentration is more at the downstream side, in the downstream direction. So hydrogen gas bubble decreases Ka conductivity of this electrolyte, and local anodic dissolution rate decreases. So as the hydrogen gas bubble evolved, so its electrical conductivity of this electrolyte actually decreases, and also anodic dissolution also decreases. So it is governed by the size and distribution of the hydrogen gas bubbles in the inter-electrode gap. So it is easy to calculate the volume of hydrogen gas evolved and effect of temperature and pressure on it. Estimation of hydrogen gas bubble sizes and their distribution under complex hydrodynamic condition in the inter-electrode gap is difficult. So these are the conclusions of qualitative studies by Landolt et al. 1970 and Hoppenfield and Kohler 1966 and 1969. They propose that bubble layers thickness increases in the downstream direction along the gap, however, decreases with the increased electrolyte flow rate. If we increase the electrolyte flow rate, then hydrogen gas bubbles concentration will decrease, and this hydrogen gas bubble concentration is there more at the downstream direction. So individual bubble sizes decreases with the increase in electrolyte flow velocity, pressure, and both, and it increases with increasing current density. If we increase the current density, this size and concentration of this hydrogen gas bubble also increase. And it decreases with pressure with increase in the electrolyte flow velocity. Gas bubbles are concentrated near the cathode, not dispersed uniformly throughout the inter-electrode gap. So gas bubbles may form due to the evolution of oxygen at anode and due to the cavitation phenomena also, but it is not considered here. So to incorporate the effect of temperature and hydrogen gas bubbles on electrolyte conductivity, electrical conductivity of this electrolyte, so this K or electrical conductivity of this electrolyte is equal to K0 into 1 plus alpha into del T, this temperature effect, into 1 minus alpha b whole to the power n. So, this term is actually multiplied along with the existing term here. So, here alpha b is the Voigt fraction, n is the exponent. The value of this exponent actually depends on the distribution of the voids in the interelectrode gap. So, for uniform distribution, this value of n is 1.5. For non-uniform distribution, when the bubbles concentrate near the cathode, value is n equal to 2. So, for average case, actually n equal to 1.75 is considered for most of the cases. Okay. So up to this, we shall complete today. So, in the next session, we shall discuss electrochemical grinding, shape tool electrochemical machining, and other electrochemical machining processes. Thank you.